Today, we're going to look at unconstrained minimization. So that's how do you minimize a smooth convex function. So that's what we're going to look at. And we'll start with just some basic ideas and definitions about what it means to minimize it. By the way, most of these problems don't have they don't have analytical solutions. So we're going to come up with algorithms that only in the limit actually achieve what you want. But that's good enough for any practical purpose. We'll talk about what is basically the most obvious and the most famous algorithm. That's the gradient descent method, where you just evaluate the gradient and, roughly speaking, go downhill. Steepest descent is a variation on that. And then we'll get to something quite interesting, Newton's method. Well, the very name suggests that this is not new. But we'll see the important thing about Newton's method is we'll understand how you get an algorithm that exploits not just a first order gradient, but also a Hessian as well. These methods, probably you've seen it. I hope you've seen it in some other context. And you might know about what you might know about Newton's method is that once it gets close to the solution, it converges to extremely high accuracy very quickly. And we're going to analyze that very much. Then what we'll do is we'll switch gears. This is obviously not new. I mean, it is, after all, Isaac Newton's method. So then we'll switch gears and we'll talk about something which is actually quite modern. It's a theory only 10, 15 years old. And that's the theory of self-concordant functions. This is pioneered by Nesterov and Nemirovsky. And so we'll talk about that. And it's a new way to analyze Newton's method. And it's the method that will be successful later in the course in showing that the methods we're going to look at, interior point methods, actually have polynomial time complexity on convex optimization problems. Finally, at the end, we'll say a little bit about implementation. We'll tie the ideas of this section. We'll tie all of this together with the ideas of numerical methods that we discussed in the last lecture. And in particular, particularly interesting will be topics like this. How do you exploit structure in solving the linear equations that you'll have to solve when you implement Newton's method? And that'll be a very interesting topic. So we're going to look at smooth unconstrained minimization. So we're going to minimize an objective function, f, and we're going to assume it's convex and twice continuously differentiable, right? So its domain is open. And we're going to assume that the optimal value is attained, right? The only other option, of course, is that it's minus infinity, it's unbounded below. Actually, all the methods we're looking at will do the right thing when it's unbounded below. We'll see how that works, but we're just going to assume we're in the case where we assume it's bounded below and attained. And so the idea, the goal, is to produce a sequence of points where f of xk goes to p star, right? So that's the idea. And by the way, even when it's unconstrained, it's the same statement, right? So you produce an unbounded sequence. I mean, that's a bit silly because when you run an algorithm, it terminates at some point finite. It'll run out some maximum number of iterations and produce a function value that's very, very low. Okay, and you can interpret a method that produces a minimizing sequence. That's sometimes what people call a sequence that does this. You can interpret that actually as these are iterative methods for solving the set of equations which are the optimality conditions. It's the gradient equal to 0, right? So that's the other way to interpret it. And in fact, for several of the algorithms, we'll see both interpretations are quite illuminating, right? So, okay. Oh, and I should mention one thing. We're going to look almost exclusively at iterative methods. There are a handful of problems where there's some sort of like silly analytical solution. I mean, some of them are important. One is least squares. Right? So you don't need an iterative method to solve least squares. So that's an important building block. Of course, minimizing a least squares problem or something like that, that's linear algebra, right? Because the optimality condition is the gradient equal to 0, and that's a set of linear equations, and so you know all that already. There's nothing to say. But we're mostly interested in cases where that's not true, and so you'll need an iterative method to solve it. Okay. Now there are a couple of assumptions. I'm not going to go into it in huge detail, but they're actually important to understand. So the first thing is you have to have a point that's in the domain. So you have to start with a point in the domain. Often that's easy. If the domain is all of Rn, it's nothing. You pick your favorite point. If the domain is, r plus to the n, that's again very easy. You might start from the vector of all ones. But actually, in some cases, it may not be easy to find a point in the domain. We will later see methods that would work even if you don't know a point in the domain. So we'll see that later. Another very important thing is we're going to assume that the sublevel set, the initial sublevel set, is closed, right? And this is basically going to, prevent the algorithm from having x, go towards a point which is not in the closure of this, and that would, okay, that's a pathology. Now, it turns out this is generally quite hard to satisfy, but one simple sufficient condition for that is that all sublevel sets are closed. And that, by the way, some people simply say f is a closed function. That means epi f is a closed set. Okay. So, by the way, if you have a background in analysis, that's fine. And if you don't, then at least you should understand what this means intuitively, right? And you can figure out what these things mean. So now if you're differentiable and closed, it means your domain is open and the epigraph is closed. And that means you can't do something like simply have a boundary in the domain and then go straight up to infinity, right? That would be closed. That's a closed function, but it's not closed differentiable. If you have a closed differentiable function, it basically says the function kind of has to go to plus infinity. There's no other way to do it, right? You can't have something like entropy or square root where you get a pathology like this and then it stops at a finite value. That you can't do. And some conditions here that are sufficient, obviously if the domain is everything, that's fine. Another one is if the function goes to infinity as you go to the boundary, that's good enough. That's called a barrier function for the domain, and that's good enough to imply this. Right? So here are some examples. Here's a log sum x function. It's obvious because the domain is everything. The domain is Rn. Right? So of course that has closed sublevel sets. Then here's another one. This one does not. That's the log barrier for a set of linear inequalities, right? Which is AI transpose x less than bi. That's the log barrier. And by the way, this is a perfect example of a function where it need not be easy to find a point in the domain. To find a point in the domain of this means find a point that satisfies a set of strict linear inequalities, and you may have to solve a linear program to find such a point, right? So this is an example of that. But it's also an example of a point where the domain is obviously not all of Rn. The domain is an open polyhedron here. So it's the interior of a polyhedron, right? That's the domain. And in fact, this has the property that epi f is closed. And what happens here is that it's a barrier. As you move towards the boundary, if AI transpose x gets close to bi, then one of these terms gets super negative. With the minus sign here, the whole function goes to plus infinity. So, okay. So we will be using, at several times, we're going to be using basically a sledgehammer to, well, show convergence. Let me explain why. In some sense, these convergence analysis of algorithms and things like that, in this case, they're important. What they really are is they're sort of like feel-good things, right? Because you implement something in a real language and it works and stuff like that. And there's always something in there that has a max iter like 30 or 50 or something like that. And, if you hit the max iter, you're not going to go forever, right? So the kind of algorithms you have, I mean, these results that you have that say something like, as k goes to infinity, you converge to a solution, technically speaking, are not actually really relevant in practice, if you see what I mean, right? They're just not, right? Because you don't run algorithms for infinity, right? And you're not interested if the limit is, has optimal value. I mean, these are not interesting, right? So these are more like sort of feel-good things. They basically say, well, in my production code, I have this max iter thing there, but if you don't hit that, right, then in principle this would produce a solution or something like that. And so these are not bad things to say. My feeling is given that, by the way, we will see some exceptions to this later that are very impressive. So we'll see some exceptions to things that they're not feel-good things. They're actually quite explicit. But most of this stuff is just feel-good stuff. You'll see why. I'll stop and make various points about this earlier. But in fact, what it means is I'm going to feel free to take extremely strong assumptions, right? Because it just shortens the proof, and because there's no point, proving this under the most general conditions or something like that. So here's one of them. Ready? Is strong convexity. So strong convexity basically says there's a minimum curvature. It says the Hessian has minimum curvature little m. And you know, this could hold, this has to hold only on that initial sublevel set or something like that, but that's all you need, right? And by the way, if the sublevel set is bounded, this is automatic, right? Because if actually all you really have to say is that the Hessian is positive definite everywhere, then, I mean, if the sublevel sets are bounded, right, then the minimum of a continuous function on a compact set is positive, right, of a positive function. So that's, again, if you know analysis. If you don't worry about it. Okay, so this is a very strong assumption. All right, now what this does is actually something very interesting, and we'll see variations on this later. This inequality right here, that's the classic inequality that holds, right? So that's without this term. This inequality holds, of course, for any convex function. I mean, that's what it says. It says that the first order Taylor expansion is a global lower bound on f. If you add the assumption of minimum curvature here, then you can actually tighten it, right? So you can actually say plus m over 2 times x minus y norm squared here, right? So you actually get and in fact, that's really cool because what was before, this used to be an affine lower bound. You now have a quadratic lower bound, okay? Not just quadratic, but one with a curvature m. Right? All sorts of implications here, right? So for example, if I minimize over y, the right-hand side, it's a quadratic function in y. It has a lower bound. I mean, there's a number, right? And in fact, if you do that, you immediately get the following bound, which says this. It says that f of x minus p star is less than or equal to 1 over 2m times the norm of the gradient squared. I mean, that's actually very useful as a stopping criterion. Again, in a feel-good way. And the reason is that you don't really know m in practice, right? So the actual code says, you know, if the norm of the gradient is less than 1e minus 7, right, or something like that, it says break. That's what's actually in the code. And someone looks at that and says, well, what's that all about? And you would point to this as the justification. You might even put this in the comment in the code, right? Only minor problem is you don't know m, right? So that's why I would call this a feel-good thing. Okay? So that's the idea. So biggest class of methods, not all methods, but a very big class of methods that are called descent methods. And we'll look at them completely generically. Looks like this. It says that your new point is going to be your current point plus a scalar, which is going to be positive, right, times some direction vector. And it's typically written something like delta x. I mean, people write it other ways, but anyone would understand this, right? And it's a descent method because when you run this method, the function value goes down, right? So it says that at every step, your function value goes down. Now, whenever you have an iterative method, and especially have one that actually works, the analysis of it usually hinges on some quantity which is decreasing, right? And so, well, if you want to minimize f, this is the most natural quantity. It says, so you say, what do you do? What is your algorithm doing? It's minimizing f, and it has the property that every step it takes, f gets lower. Oh, by the way, unless you're at the optimum point. If you're at the optimum point, the gradient is 0 and you break because you're done, right? Otherwise, it produces a point that's better. So basically, the algorithm has the control flow looks like if not optimal, then produce a better point. Better means lower function value, okay? Now, by the way, you might think that it has to be this way, but that's not true. There's many names for the function that goes down, for a function that decreases during an algorithm. And in fact, they have lots actually for all algorithms, usually there's something like this. And it doesn't have to be f. Another function that could go down that's used all the time is something like the norm of the gradient. And that would do the trick too, right? It says that because what you're trying to do is find a point with 0 gradient. You'd say, well, this algorithm does the following. If the gradient's not already 0, it produces a new point with smaller gradient. That's it, right? That's kind of the idea. So it doesn't have to be f. And we will later see algorithms for which something like this or something more complicated, but in this spirit, closer to this, actually goes down rather than f. Okay. Now, and this is written lots of other notations. Something like this. That's some kind of like pseudocode assignment or something like that. Or it might be written this way to make lighter notation. If you don't want to have k's and k plus 1s floating all around all over the place, x is sort of the current point. X plus is reasonably standard notation for the next iterate, right? And you just get cleaner notation. Okay. Now, if in fact f of x plus is less than f, so it's a descent direction, that says that the inner product of the direction you stepped in, that's delta x, and the gradient has to be negative. Okay? So, and such a direction is called a descent direction, right? So here's a generic scheme. It's a gradient descent method, and it looks like this. You're given a starting point in the domain, and at each step you determine a descent direction. Now that we have to instantiate that to make this a real algorithm. So this is like a prototype, right? So it says you find a descent direction. We're going to see tons of ways to do that. Okay. Then you do a line search. Again, tons of ways. But you have to choose t so that this holds up here, and possibly some more, right? And then you update. And then you do this until a stopping criterion is satisfied. And in fact, the real control flow in a real algorithm doesn't quite look like this, because the stopping criterion usually involves something. Actually, when you calculate this, you would do something like look at its norm, and if the norm is less than some tolerance, you'd break. So the control flow doesn't look exactly like this, but it looks close enough to this. Okay, this is the idea. Okay, so to instantiate, to make a real algorithm out of this prototype, we have to say, how do you compute this? How do you compute the search direction, and then how do you compute the step size, right? And there's actually a couple of surprises on each of these. So I will, we'll get today. There's going to be maybe one or two surprises, things that are just non-intuitive that you might not know, and they're just things that you wouldn't know it unless you actually tried a bunch of these things. Okay, this is good. There's going to be a punchline here, which is one of them. So here's some line search types. One is an exact line search. So it says, hey, you know what? You're trying to minimize f. You specified a direction. Then x plus t delta x is, well, t is positive, so that's a ray. And so what you simply do is you say, well, along that ray, I'll choose the minimum value of f. Okay? I mean, that's what you're trying to do. You're trying to minimize f, so why would you not do that, right? Now, by the way, that means you've restricted that convex function to a line. Oh, and we should probably deal with that right away. How do you minimize a convex function of a single variable? Yeah, binary search. Yeah, that's it. So you just do bisection. That's all. So there's no issue there. You don't have to know anything. You just do binary search. So this would be done with binary search, for example. Okay? Or I guess we call it bisection. Okay. Here's something at the other end is extremely simple. It's called backtracking line search, and it's got other names depending on your cultural background, right? So it's also called an Armijo search, a Goldstein search, and an Armijo-Goldstein search, and probably many other things. You'll see this line searches like this in Spirit all over the place. And it's this. It says something like this. You take two parameters, an alpha and a beta, and what you do is the line search starts like this. You start with a step of 1. By the way, all of this can be changed. You start with a step of 1, and here's what you're going to do. This is the convex function, which is restricted to this ray. And so if you did an exact line search, you would pick that t, something like that. That would be the exact one. Okay. Now instead, what you do is this. If I look at the function f of x plus t, and then the inner product of the gradient with delta x, take alpha equals 1 in this expression. That is actually, that's the affine lower bound on the restriction function, right? That's plotted here. So this is where you are. That's t equals 0 right here. So you're at t equals 0. And then this function here is this thing, right? It's that thing with alpha equals 0. Now that's a lower bound on your function. So whatever your function is, it's above that. Okay? By the way, that means there's no t that would ever get you a decrease as big as this, right? So that, because it's a lower bound. So here's what you do. You degrade that lower bound by a factor, and the factor is alpha. So if alpha is 0.5, it says you take half that slope, and you get something that looks like this. Okay, this might be for, yeah, it could be alpha equals 0.4 or something. I don't know what it is, right? So you take alpha equals 0.4, and that's this thing. Okay? Now, this one has the following property, that there are plenty of t's where you will get a decrease at least as much as this. Okay? And then that's the algorithm says you start at t0, t whatever, 1, it could be anything you like. And then you simply multiply by beta until this inequality holds. And I think that's called maybe the Armijo condition, or I guess if you're in Moscow, it's the Goldstein condition or something like that, right? So that's the idea. Now, when you look at this, so here's going to be the first surprise. Here it is. When you look at this, you would say, whoa, the exact line search has got to be way better, right? I mean, because a typical parameter value for beta is a half, right? So the only step lengths you ever take are one, half, quarter, eighth. I mean, this looks very crude. By the way, alpha can be all sorts of weird things. Here's a very common value of alpha, unbelievable, 0.01. So that basically says if the minute I get 1% of the decrease predicted by the linear extrapolation, I'll take it. Okay? I mean, this sounds, you're not coming close to doing an exact line search. And the exact one, I mean, the picture, all your intuition suggests an exact line search would work way better. Guess what? That's false. It doesn't work actually any better. I mean, it does for silly little problems in like 3 dimensions or 5 or 15 or something, right? But for any real problem, it turns out in fact, quite often, the backtracking search works not just as well, but actually often better. Now that's bizarre, and there's no way, I actually don't even really have any particular intuition to explain that, but it's true. Okay, so here's gradient descent method. Here's our first fully instantiated method. Oh, and I might add, it's due to Newton without the backtracking. But anyway, so here it is. It says what you do. So the search direction will simply be negative gradient, right? And by the way, what could be more natural? By the way, we're going to find out it's not natural at all, but this is just to set it up, right? So what could be more natural? You're at x, and you say, I would now like to choose a direction where the function gets smaller, right? So you take the gradient. That's local information. And the negative gradient direction is actually the direction where the function is going down the fastest. So I mean, why would you not do this? It'd be hard to imagine not doing this, okay? So let's just start with doing this, because it's kind of the most basic algorithm and so on. So here it is. We choose the negative gradient direction, and here it is. So we evaluate the negative gradient direction. The real algorithm might have, it would test the gradient here, and if the gradient were less than the tolerance, it would break, okay? Then you do a line search. You could do exact line search, backtracking is fine, and then you update. And so this works. I mean, that's the idea. I mean, it's not hard. It is actually quite easy to show it works. And you can read through the book. And you can show various things. Like here, you could show that, for example, the objective value converges, exponentially, or towards the to p star, or something like that. Yeah. Now it turns out C is like basically 0.999999 or something like that, but that's another story. Okay. All right. Now here comes the first surprise. I mean, actually, this is used because it's extremely simple, right? And, for some problems, you will soon know why it works on some problems. But on others, it's completely useless. It doesn't work at all. Well, of course, in theory, it works. But since in practice, you're not interested in doing 10 to the 9 iterations, it doesn't work in practice, okay? I mean, in theory, it always works, okay? So you will soon know exactly why it doesn't work. But this is the first... I mean, I think this is the first thing that's not obvious, right? Because the gradient, if you didn't know anything about optimization and someone walked up down the street and said, please make up an algorithm for you, you'd make this up. I mean, I hope you would make this up, right? Because it's the most obvious thing to do, right? You say, please make me an algorithm. You can use local information, wherever you are. I'll tell you things like gradient and whatever. I hope this is the algorithm you'd come up with. And the weird part is it doesn't work that well in a lot of cases. You'll soon see why. Okay, so let's examine it. Let's take a quadratic problem. Looks like this is just an R2, just to understand. So here we have a parameter here, gamma, and we can as we make gamma big, what happens is we're changing the condition number of the quadratic form here, right? This is x transpose px. I can change the condition number with gamma, right? Because it's the matrix diag 1 gamma. And if I make gamma huge or small, the condition number gets really big, right? And so what does that mean geometrically? It means that the sublevel sets, if gamma is 1, the sublevel sets are round. Oh, yeah, please, let's discuss that. How does the gradient method work if gamma is 1? I mean, you can work out the exact formulas, but who cares? Just tell me what happens then. Here are the sublevel sets, right? like that. Here are you. Which way is the gradient pointing? It's pointing straight uphill, and then negative gradient is pointing straight towards the solution. Okay? So, gradient method works superbly when gamma is 1, right? Because in fact, the gradient points you directly to the solution. Okay? And then, so what if you're doing a backtracking line search, right? You'll cover a distance, a factor of 2 each time, and you're going to get very fast convergence. Everybody see this? Now, if you look at what happens here, this is condition number 10, actually, which is really square root of 10 in terms of the semi-axis ratios. But so here, look what happens. They're now ellipsoids, right? And what happens is the gradient, of course, is the normal to the level curve pointing uphill. So the negative gradient is the normal to the level curve pointing downhill. And so you can see what's happened is that is the direction of the negative gradient. Okay? Now, is it pointing directly? Is it pointing generally in the right direction? Yes, it is, right? It's pointed more towards 0 than away from 0, okay? But it's not pointed the right direction, right? And so what happens is you go over here, then here, and this is because for exact line search, you get exactly the same thing for backtracking line search. For exact line search, you can just work out what the iterates are, right? And so you get this kind of thing. And this actually has a name, and I forgot what it was, but it doesn't matter. So somebody's name is attached to this zigzagging, okay? Now, this picture makes it completely clear. If I made gamma, that was 10. What if I made it 10,000? What would happen? You can see exactly what would happen, right? The iterates would just go like this, right? And they'd make very slow progress towards 0, but that's what would happen. By the way, what happens if I make gamma really small? Yeah, then this thing just rotates 90 degrees. And so actually, this is your first hint. Your first hint of what's going on is that the condition number, right, of the sublevel sets is going to play a role if you look at something like a gradient method, right? That's the hint, right? So gradient method works beautifully and condition number of the sublevel sets is basically how anisotropic the function is, right? Isotropic means it's kind of the same in all directions. It means that the level sets are kind of roundish, right? Anisotropic means they're weird and have a big condition number, right? It's very different going one direction from another, right? So if the sublevel sets, if the function is kind of well conditioned, right, then what happens is gradient method works really well. Because for one thing, the negative gradient points you towards the solution, right? If it's not, if you have a big condition number, the gradient method points you somewhere that's vaguely in the right direction, but you might be making like an angle of 89.9 degrees or something like that towards the right direction. Everybody see what I'm saying? Okay, so and this is why it doesn't work. By the way, if you're really lucky and the function you want to minimize has reasonable condition number, then gradient method is going to work great for you. And that's great. Your code will be 4 lines or whatever and something like that. Everything will be fine. Okay? Okay. So let's look at a non-quadratic example. See how this works. Here's one where, the sublevel sets are not spherical. They're certainly not ellipsoidal, right? They're not spherical or anything like that. But, roughly you still have the same idea. Here, the sublevel sets they're not round, right? They're a bit wider than they are tall. Not even by much, right? That's the hilarious part. And you can see you get kind of the same phenomenon. This actually looks like it works pretty well. By the way, this is an example of an exact line search beating a backtracking line search, but this is an R2. R2 is really it doesn't even count as a legitimate problem. So, okay? So this is the idea. Now, that brings us so here would be like a measure of what F looks like. It's a problem in R100, right? And here, you can see all various things here. Oh, but this is a funny one, right? So here, you're minimizing this. That's a real problem, okay? That's a problem in R100. And you're minimizing a log barrier plus a linear function. By the way, what's kind of cool is look at all this. It hardly matters, but it basically says doing the cruder line search, you're doing better for a while. It just doesn't matter, but this is just not obvious, right? You might imagine that these were on 2 different paths and things like this. By the way, this is called sort of linear convergence. That's standard notation, and it actually means exponential convergence, right? Because this is iterations on a linear scale, and that's some kind of error, in this case suboptimality, on a log scale, right? So linear means, and the slope, of course, gives you the factor, right? It says something like this. Each iteration, you reduce your error by a factor of 0.9, you know. I mean, we could work out what it is here. I'm not going to do it, but that's the idea, okay? So that's linear convergence. Now, so let's now talk about this idea of gradient, because now you think and you realize, wow, the gradient had to do with, I don't know, what's wrong with the gradient method? And the answer is something like if the function is if it is anisotropic, or if the sublevel sets are not well conditioned. This is when gradient works badly. And this kind of hints that you could come up with something that's the spirit of the gradient method, but that actually adapts for the geometry, or, you know, that has a different geometry, right? And it turns out that's correct. So here's what you do. It turns out if you ask the very simple question, if you're sitting at a point X and you say, what's the fastest way downhill? You ask someone for directions, right? And they point. You would think there's really only one way they can point, which is the negative gradient. It's reasonable, right? It's actually wrong, because it turns out there's actually a cultural bias when you ask which is the fast way. And it's not a cultural bias. What it is, it's this kind of bias. It depends on the metric you're using. If you change the metric and ask someone what's the fastest way downhill, you get a different answer. Okay? It's weird, but it's true. You'd think, what's wrong with minus partial f partial xi? I mean, how could that not be? That will be, in fact, the fastest way downhill if you're using a Euclidean norm. If you're using an L infinity norm, or a weighted norm, or some other weird norm, that's not the fastest way downhill. So that's the topic we're going to look at. It's actually interesting, and it's important to understand that the gradient, well, I guess if you know about physics and things like that, the gradient, it changes when you change coordinates, right? So, okay. So let's see how that works. So let's take any norm, not necessarily a Euclidean norm, and then what we're going to do is we're going to say that the steepest descent direction is this. You say, find me a direction of norm 1, and that's where the norm comes in, because that's how you're normalizing, that minimizes this thing. That is your linear approximated decrease in f. Okay? Now, if this were the 2 norm, the answer would be the gradient scaled, right? Because scaled to have norm 1. It would be the gradient divided by the norm of the gradient. That's what it would be. But what's weird then is if you walk up to someone using a different metric and you say, please tell me what's the fastest way downhill, if they're using a different metric, they'll point in a different direction, right? And the reason it just has to do with efficiency, right? If in their metric distances this way are long, I don't know, they might point you there, because according to by their idea of efficiency, or how steep the descent is, that's better than simply following the negative gradient. Okay. So this is the normalized steepest descent, because the thing has norm 1, and then often it is unnormalized, and it's unnormalized by multiplying this, which has norm 1, by the dual norm of the gradient itself. And what that does is it makes sure that the inner product of the gradient and the normalized the unnormalized steepest descent direction is minus the norm of the gradient squared with the dual norm, right? And that actually makes everything work with things like the 2 norm. And this would agree with the 2 norm, things like that. So steepest descent method is basically general descent method. You choose the steepest descent, and it's just like gradient descent. Basically, the summary is it works. Okay. But what's very interesting now is this is really a family of methods, because for every norm you get a different method, and you get some interesting ones. So let's look at a couple. If you get the Euclidean norm, it's identical to the gradient descent method. But suppose you use a quadratic norm. This is going to be extremely important, so we're going to get to this. If you use a quadratic norm, so x transpose px to the 1/2, right? Then it turns out that what you use is the negative gradient, but then multiplied by p inverse. Okay? Now, that's positive definite matrix. It doesn't rotate things more than 90 degrees. So it's a descent direction, but it's different, right? It's minus p inverse. And we're gonna get to that. I'll come back to that in a minute, but actually I'll say another very cool thing about it. If you're going to use the steepest descent with a quadratic norm, with norm p, it's completely equivalent to doing the following. Take the original problem and change coordinates by p minus 1/2. If you change coordinates by p minus 1/2, then this p norm actually becomes in the new coordinates the norm, and its steepest descent. So what that says is, sorry, it's gradient descent. It says that steepest descent with a quadratic norm associated with p is identical to the following. It's exactly the same as doing the following. Take your original problem, change coordinates to make this metric I, and then apply gradient descent. So in other words, it's not much different. It just says change coordinates. Okay. We'll come back to that in a minute because that tells you exactly how you want to choose the change of coordinates, right? So, okay. And okay, let's look at another one just for fun. If you take the L1 norm, you'd say, well, what's the steepest descent direction? And it turns out you can always choose the steepest descent direction to be an EI. So it's something like that. And in fact, so it's an algorithm also invented in every field periodically every 10, 15 years or something. It has a name in every field. Sometimes it's like, I don't know, if they do it in blocks, it's like, I don't know, scalar something descent. I don't know, block descent. So it does this. It says you will only update one variable xi, one coordinate at a time. And so what you do is you get the gradient, you look at the components of the gradient, you find out which is largest, and then you go in the appropriate direction. You either increase or decrease depending on whether the sign of the partial derivative is positive or negative. Everybody got it? And that worked. And that's just steepest descent in the L1 norm. Okay? And the picture would look something like this. So that would be the negative gradient. But here, if I use steepest descent with a p norm, and that's the ellipsoid, it says you're not actually going in this direction. What you're really doing is you're solving sort of a linear program. You're saying, please go as far as you can in that direction, staying in here. And the solution is here. And you can see that, in fact, you're going in a different direction, right? Now, the direction is never more than 90 degrees away. It's not even 90 degrees away, right? It's a positive definite matrix. So the idea is that if you do steepest descent with a quadratic norm, p, it says that actually you have distorted space and it bends the gradient descent method. It will bend it to another direction. Okay? So I'm saying all these things. You don't have to, I mean, these don't even have like perfect meanings, right? So I'm just talking about this at the idea level because we're going to get to something and it's going to be kind of obvious. So let me ask you the following. You can choose P for a problem. How roughly do you think you should choose it? I mean, two ways to think of it, right? One way to think of it is you should choose P so that the ellipsoid P kind of matches the shape and dimension of the sublevel sets. Now, the sublevel sets are not ellipsoids unless the problem is quadratic, in which case you can minimize it by solving linear equations. But just roughly, you would choose it so that the ellipsoid defined by P kind of has the same shape and stuff like that. Alternatively, you would choose P so that P to the minus 1/2, if you transform by P to the minus 1/2, the sublevel sets of the function become round to the extent possible, right? Now, they're not going to be ellipsoids, so they're not going to become spheres, right? But you kind of, and in fact, some people even refer to that as rounding. So this tells you about how, now you have the intuition about how you should choose P. So let's look at an example. I mean, it's a silly example in R two, but it actually shows what happens. Okay, so here it is. Here's this nonlinear function. These sublevel sets are not ellipsoids, but roughly speaking, the sublevel sets here are wider than they are tall. By the way, not by even a big factor, okay? And here, if you choose this would be a good choice of P, right? P here, a good choice of P would be to have these ellipsoids kind of align with the sublevel sets of the function, in which case, I mean, you can just sort of visually see it, it's doing well, right? Here's a case, that's a bad choice. That was worse than P equals I, right? Because it doesn't get the right way. Now, another way to think of it is the following. When you're choosing P to have the ellipsoid like that, that's the same as scrunching space this way, right? Because that's what it means. It says that if you believe that if you believe sort of like that distance is the same as that distance, if that's your view of things, then the correct way to think of that is to take this image and scrunch it. That's, by the way, transforming by P minus 1/2. Okay, that's rounding it, right? And if you round these things, you will see they get more spherical, right? less condition number. Less condition number means gradient's going to work well. Okay? So here, basically it says, if this is your opinion, if that's the metric you're using, then what this says is, if that's the metric you're using, it says that basically what you should do is take those images and crush them like this by a factor of 2. And they're going to get more elongated, and gradient's going to work much worse. Everybody following this? So, I mean, this is all, okay, fine. Okay, so what this says is choice of metric has a very strong effect on the speed of convergence, right? So if you're doing if you have some problem and condition number is, fine, go ahead and use gradient. But otherwise, the choice of the metric, actually what it says is, if you do an affine change of coordinates of your problem, then it has a first order effect on gradient. In other words, it can make it go from working well to terrible. In fact, usually it does that. Of course, if you're really good about your choice, it can go from terrible to good. But if you're not good, it goes usually from good or okay to terrible. Okay? And this brings us to your suggestion, which was let's adapt. Let's do steepest descent, but let's actually change the metric every time. And it'll always be based on our best guess of actually the curvature of the function. By the way, there's lots of ways to do curvature. This is only one of them. Other ways are much more sophisticated. But this is one. So here it is. It's just this. What we're going to do is the Newton step is going to be negative gradient, then multiplied by the inverse of the Hessian, right? You can see this makes total sense. This says if you're minimizing a function, you're at a point x, and someone says, what do the sublevel sets look like? The answer is, I don't know what the sublevel sets look like. Of course I don't know, because in fact, all I have is a gradient and Hessian oracle. The only thing I'm allowed to do is call 2 methods, 3, maybe 1, that gives me 3 things. I query the function at a cost, and I get the function value, the gradient, and the Hessian. That's it. I don't know anything else, right? I mean, I may have some other information, but that's not fine. So if I do that, you don't know. But actually, a very good guess, if you're near the solution, is the Hessian. Hessian tells you everything, because near the solution, all convex, smooth convex functions, near the minimum, they all look quadratic. And the sublevel sets are exactly given by the Hessian. So that seems like a good choice, and that's exactly what the Newton step does. Okay, so lots of other ways to interpret it. Here's one. One says, well, let's take the function. Let's form f hat at the current point. And f hat is going to be the second order approximation. So that's the first order approximation, and that's the second term in the Taylor series. And then it says, I'll take this second order approximation. It's a convex quadratic. I'll minimize it. And you know what you get? The Newton step. So that's the Newton step. Another way is to say, I would like to find a v so that the gradient of f of x plus v is the step. I want that to be 0. But I don't know how the gradient changes, right? Oh, if the gradient were affine, I would know exactly how to calculate v, but that's the case of the function being quadratic, which means I can solve it just by solving linear equations. So I don't know. So what I'm going to do is this. I'll say, well, what is a good approximation of what the gradient is if you step v? The answer is very simple. It's the current gradient plus the derivative of the gradient, that's the second derivative, which is the Hessian, multiplied by the step you take. And so that is the first order approximation of what the gradient will be at x plus v. And so you don't know what the gradient is at x plus v, but you want it to be 0. But what you have is this approximation. So you set the approximation equal to 0. Here, solve, you get the Newton step. Okay? So here are the 2 pictures. They're different, but they both suggest some very interesting things. Here's a function f, just in 1 dimension. I'm minimizing, so here I am. And Newton method does the following. It fits f hat, which is the quadratic approximation. By the way, f hat does not have to be above f. It could go below it as well, or it doesn't have to be above. In this example, it is, but okay. So, and then you take the minimizer there, and then that's the Newton step. Okay. Here, this is the derivative of that function, and what it says is you're here, and what you want is you want to find the crossing of f prime with 0, because that's what f prime is, the gradient. You want the gradient equal to 0, so you want the crossing. You're here, and it says, please find me a point, get me a point where you have the 0 crossing. The answer is you do a linear extrapolation. This slope is exactly the second derivative, right? So that would give you this point, okay? And now I'm going to ask you, this is just geometrically, I don't want to hear anything else, just geometric intuition. If you repeat, what is going to happen on the next step of Newton's method? We can talk about it on the left or on the right. Let's start with the left. What happens on the next Newton step? You start from here. You have moved closer to the minimum, and the next step is you're going to form a new quadratic model, but now around here. When I form a quadratic model around there, it's going to be way better than this one, right? And so the next step is going to be very good. By the way, when you get near the bottom, how good is the quadratic approximation? Very, very good, right? Because that's informal speech for it's at least quadratic good, right? Okay, right? So, and what happens here? What happens on the next step here? On the next step here, when you want to, your next estimate of the zero crossing is going to be excellent. Why? Because when you have a smooth function that's going to cross 0, right, and you're near where it crosses 0, the linear approximation is excellent. And therefore, your next estimate will be good, and then the one after that is going to be like stunningly good. Okay. But all of this is just sort of, it's very important to have the geometric intuition, right? So what this suggests is this: if we do this thing where we update the metric, or however you want to call it, if we do something like a Newton step, this is going to work. We're going to see something very shocking happening at the end. We're going to get to that. Oh, by the way, here's a very perfectly interesting method. It goes like this. You evaluate the Hessian at the first point, just once, right? You calculate, you know now. You do a Cholesky factorization of the Hessian of f at x0, period. And then you simply change coordinates once and do gradient descent in that new thing. That'll work. That actually, if your initial point is okay, that'll work incredibly well. But this is adapting at every step. Oh, and there's all sorts of other cool things, like you can adapt it every 10 steps. You can update it. You can update it every 30. There's all sorts of things. Another interpretation is this. The Newton step is simply steepest descent in the local Hessian norm, right? So what you do is you have a norm induced by the Hessian, and you take the steepest descent in that metric, right? So, and that's what you get. Okay, so, all right. So one of the things you get is, and I'll explain where this is all headed and some very interesting attributes of it. But so this is lambda of x, right? That's called a Newton decrement. And here's what it is. It has lots of interpretations, but it's a measure of the proximity of x to x star, right, to the optimal point. And what it says, it's a very good estimate of f of x minus p star, right? Assuming you're close. If you're close, this is basically, it says you form the quadratic thing, and you ask yourself, how much is the quadratic going to go down? The answer is exactly lambda squared over 2. Okay, so that's what it's. So lambda squared over 2 is very small. That may or may not predict the actual function going down, but to the extent that it does, it's a very good estimate of how far off you are, right? So in fact, stopping criteria based on lambda are actually way better than based on the gradient, right? If you remember, the gradient, the relation between the norm and the gradient and how suboptimal you were involved that 1 over m, which you don't know, right? So this one actually gives you a number that you can trust, right? And it's not a feel-good thing, right? Well, this one is because it depends on the third derivative. We're going to get to talk about that too, okay? So, but it's way better than just saying the norm of the gradient is small. Okay, now it's got all sorts of other interpretations. It is the norm of the Newton step in the quadratic Hessian norm. So that's another way to say it. And it's the directional derivative. So if you remember in the Armijo line search or Goldstein line search, there's that slope, which says, how fast are you going down? And the answer is it's minus lambda squared, right? Which once again tells you if lambda squared over 2 is tiny, it says in your line search, it's not going to go down much, right? So that tells you that. Okay, now this is very important, is the following. This measure of proximity of x to x star is affine invariant, okay? Affine invariant means if I take my problem and if I change coordinates with an affine transformation, and the simplest one that does the trick is you scale the variables, That's all. You just scale the variables. Instead of x2, you use 50x2. Instead of x7, you use 1e minus 6 times x7. Okay, that's scaling the variables, right? Okay. Now, that's an affine transformation. The steepest descent, the gradient descent method does not commute with affine changes of grade. It is not affine invariant. Affine invariant means that some operation or an algorithm is invariant under, you get a commutative diagram. You change coordinates, you change coordinates, run the algorithm, or you run the algorithm, change coordinates, you get the same thing. That's false for gradient descent. Okay? And we already knew that, because in gradient descent, if I change the coordinates, it's gonna absolutely completely change the geometry of your set. And if I change them in a benevolent way, I can make the convergence faster. If I change them in a not benevolent way, I will bring your gradient descent method to a halt. Not a halt, but I'll make it so slow that for practical purposes, it's useless. Everybody got this? By the way, among changes of coordinates, there's a lot more bad ones than good ones, just so you know. So, right? Everybody got this? Okay, so this measure is actually affine invariant. That's very simple to see. By the way, the Newton step is affine invariant. The Newton algorithm is entirely affine invariant. Why? Well, because if you change coordinates by t, the gradient transforms like t times the gradient or something like that, or t transpose, and then the Hessian undoes that, because that transforms as like t Hessian t transpose. When the smoke clears, the t's are gone. There's one t left, and you get a commutative diagram. Okay, so Newton method is actually invariant under scaling, right? Gradient method is very much not invariant under grading, under affine transformation, okay? And this stopping criterion here, if you base it on lambda, invariant under changes of coordinates, which is actually very cool, right? Because the other one will ruin, I can break any algorithm that has, if I grep through the code and find if norm of something is less than this, I can break that code so easy it's not funny. All I have to do is all I do is I take your problems for which it's working, I scale the variables in some way, and you'll either stop on the first step or you'll never stop or something like that, and I can break it super fast. You cannot do that with a Newton method, right? So, okay. Here's Newton's method. It works like this. You compute the Newton step and the decrement. So you compute this and that. And the real stopping criterion would be right here. If lambda squared over 2 is less than a tolerance, break. That would be the real control flow would look like that. Oh, okay, sorry. Our algorithm here says that. Fine. Then you do a line search. And you can choose it by backtracking. That's fine. And then you do an update. And so this algorithm is affine invariant, right? So another way to say this is that the scaling doesn't matter. Well, it matters, but it's a second order issue, and it matters only to the extent that your linear algebra will be stressed. But certainly you can handle things like condition numbers of 10 to the 5 with no problem, right? Whereas a condition number 100 will bring a gradient method to a halt for practical purposes, right? So and there's just a huge gap in how much scaling you can do. So, okay. I mean, it's something like the difference between fixed point numbers and floating point numbers, right? I mean, that's qualitatively. I mean, I don't want to push that too far, but it's something like that, right? That, if you're writing a fixed point algorithm, boy, do you have to be careful not to overflow and underflow and all that kind of stuff, right? If you're writing something with floats, yeah, I mean, it can actually tolerate some pretty big ranges. Now, you can still overflow and underflow and write a terrible algorithm, but it's a whole lot harder than if you're doing something with floats than with some fixed point numbers. It's way easier to be in trouble. A fixed point algorithm can work perfectly, provided you've had incredible care to set everything up and scale everything correctly. But you're using floats, you got much more leeway. So, I mean, this is just very rough, and I don't want to push it too much, but it's something like that. Okay. What we're going to look at now is the classical convergence analysis. This is due to Kantorovich. And that's of Newton's method. And so we'll look at this. And actually, before we start, here's what I'd like to ask you. So some questions. My first question is this: how well does Newton's method work for quadratic functions? Perfectly. It's one step, right? Because, I mean, here's an abstraction of Newton's method. You call the method get quadratic approximation at a point, you get the quadratic approximation. It's actually the function. You don't know it, right? And then it says, okay, I minimize the quadratic approximation, and here's my next x. It's actually the minimizer. So the answer is quadratic, one step. Okay? So now if a function, now what if the Hessian is changing slowly? Or suppose in fact the Hessian doesn't change very much as you move x around. It's not a quadratic function, but it's changing very slowly. That suggests Newton's method is going to work unbelievable. That's the kind of function Newton's method will just work unbelievably well on. By the way, it comes back to your suggestion, which is that Hessian is actually a heuristic for saying, I'd like to change coordinates to get the sublevel set. You don't know the sublevel set, and you use the Hessian as an approximation, right? So the current local Hessian. And so if the Hessian doesn't change much, right, as you move around in space, that's where Newton's method is going to nail it. And the extreme is the Hessian doesn't change at all. That's called a quadratic function, one step. Okay? So this is just intuition that suggests the following. How fast the Hessian changes is what's going to determine whether Newton's method works well or not. And so sure enough, guess what comes up? What comes up is exactly the Lipschitz constant on a Lipschitz constant on the second derivative. By the way, if you like, you can talk about the third derivative, right? Because L is something like the maximum of the third derivative, okay? And there are people who work this out in terms of f, d cubed f, okay? Now, we're not going to do that, but you should understand what L means. L is a bound on the third derivative. Now, the reason, I'll tell you why we're not going to do it, because the third derivative of a function, of a real valued function on Rn is actually a third order tensor, right? And so unless you're trained in this, maybe in mechanical engineering or something like that, or physics, it can cause severe headaches to consider. So I don't recommend. It's a trilinear form. And so, the fact is that, you know linear algebra, you take all these classes on statistics, probability, mechanical engineering, and a lot of matrices come up, so we all have very well developed ideas about matrices and things like that. And third order tensors, only a very small number of us are cool with. Right, and the rest of us just get a headache. So I'm just saying that's why we're going to use Lipschitz condition. But you should understand what L is. It's the third derivative. That's what it is. By the way, that model goes back to why Newton works well. If the third derivative is small, that tells you Newton works well. Why? Here's one explanation. Newton method says this. Call the following method, get quadratic approximation. If I get a quadratic approximation, what's the next term I'm missing? The cubic, the third derivative. So if the third derivative is small, I mean, I'm waving my hands, but the third derivative is small, you know what it means? It means that second derivative approximation was pretty good. Okay, so again, so all of this is this is totally obvious. There's nothing hidden here. There's nothing deep here. It just says we expect Newton's method to work well when the third derivative is small. That's one way to say it. Here's another way. The second derivative has a small Lipschitz constant. Okay, that's all. There's nothing. That's obvious. Okay, so back to the analysis, which is due to Kantorovich. Okay, so it says this has it has a Lipschitz constant L, and then the analysis of Newton's method basically breaks into two portions, right? So, and I'll say what they are. Sometimes it's called the damped and the undamped phase, and I'll explain what it is. It says the following: there's a constant eta, and if the gradient exceeds eta, then here's what you can guarantee. A Newton step with backtracking, right, will go down by a fixed number, gamma. At least, maybe more. Okay, so that's what that's called. Some people call that the undamped phase of Newton's method. Then there's this. Once the gradient gets smaller than a number, which it must because you can't execute this first step too many times, right? In fact, if it goes down by gamma each step, then you really can't execute that more than whatever it is, f of x0 minus f star divided by gamma steps. You can't do any more than that, right? So after a finite number of steps, the gradient norm will be less than eta. And at that point, the following occurs. The norm of the gradient at the next step, actually, another thing happens. In backtracking line search, you will take a step of 1. Okay? You'll take a step of 1 in Newton method. You will not backtrack, number 1. And number 2, the gradient at the next step will be less than, ignore the constant in front, but it will be less than the norm of the gradient at the previous step, at the current step, squared. Okay? Now, when this is less than 1, That's very good. That basically says that, I mean, so now very roughly it says that when you get into, so this is called, this has lots of names. One is, it's the undamped phase, it's the region of quadratic convergence. We'll see why in a minute. But what it says is very interesting. It says, I mean, and roughly speaking, it says when you get into that second phase, every time you do a Newton step, the number of significant figures is very rough, doubles. Okay? So if you have a 0.01 point, accurate point, you do a Newton step, it's now 1e minus 4. Then it's 1e minus 8, and then it's all over on the next step. Okay? Everybody got this? By the way, this fits our intuition perfectly about, you just go back and look at these pictures, right? I mean, over here, that fits this stuff really well, right? Once you're down near the minimum here, the quadratic approximation is superb, right? When you are near the crossing point, if you zoom in on it, all you see is a straight line like this, right? I mean, it's got a small curvature, but this method of following the tangent is going to get you from a good point to a superb point to like a really superb point. So it all kind of makes sense that that's how this works, right? I mean, I think this kind of, the intuition is clear. Okay. So in the damped Newton phase, most iterations are going to require backtracking, right? The idea is, I already said this, the function value decreases by at least this value gamma. And this can only go that number of iterations, right? So in the quadratically convergent phase, that's once the gradient gets small enough, no damping whatsoever, and what will happen is this will converge to 0 quadratically. Quadratically means on a log plot, on a semi-log plot, you'll actually get a quadratic. So the idea is that the number of iterations is less than something dependent on how suboptimal the first one is, right? And then the second term is log epsilon 0 over epsilon, right? So why? Because if you're doing quadratic convergence and you invert what that means, it's log, right? So, okay, and so now this second term, it's small, it's on the order of 6. And in fact, for a long time, I used to go around and give talks, and I would write 5 for log epsilon 0 over epsilon. And I did it just to bait people who were complexity theorists. Anyway, so this analysis, this is the classical analysis of the Newton method. But now I want to say some bad things about it. The good news, it's a feel-good thing. It says it always works, and it says eventually the convergence is like super fast and all that kind of stuff. And this is what this is correct. I mean, it works something like this, and you get a lot of insight, like these two phases and all that kind of stuff. It's good. Now, I do want to make fun of it though, because this is your classical. I was going to say your classical Western analysis, but unfortunately this came from Moscow, so I can't say that. But it is kind of like your classical Western analysis of an algorithm goes like this. It says if, and then you have a whole lot of hypotheses, hold, then, and then you have a conclusion. Now, if you look at the whole lot of hypotheses, not one of them is actually verifiable in practice. Not one. It would be like you have a Lipschitz constant, you have a strong convexity constant, you have all sorts of crap there. Not one of, there would be almost no circumstances where you know them, right? Except if the function is quadratic, but then it's stupid because how do you minimize a quadratic? You solve linear equations. Everybody see what I'm saying here? Okay. Then you look at the conclusions, and the conclusions would be kind of goofy. They would say things like, if the conclusion would be something like, a limit point if this algorithm is optimal. But yet that's not how, you don't, that's, Java doesn't have limit points, accumulation points, right? I mean, you have a maximum number of iterers, and that's it, okay? Everybody see what I'm saying? So that's the classic one. And then you point out that, in fact, that theorem, which someone then spends like 2 lectures proving, with everyone sleeping, then you point out it's actually totally useless. And they say, no, you don't understand. You don't get it. This is kind of to make you feel good. It's kind of so that this is, then we run the code, and, and then this is the conceptual framework and base. Anyway, okay, everybody got this? Well, let me point out here something here. Suppose you want to run Newton's method to find out, I give you a function, like one of these log sum x things or a barrier, and I want to find out how many steps is it going to take. Give me an upper bound of the number of steps Newton's method's going to take. And they go, hey, no problem. We've got this theory. Look, now look, they look down here and they say, right there's your number. Now, number 1, epsilon 0, you don't know it because it depends on all sorts of crap you don't know. You don't know m, you don't know l. Okay? So you don't know epsilon 0. Fine. Fortunately, log epsilon 0 over epsilon is basically 6 for all reasonable values of epsilon 0, so it doesn't matter. Okay? All right. Now look at the first term. Again, you don't know, well, you could, let's pretend you know gamma, okay? The first term says, there you go. That's the number of steps. It depends on how suboptimal they are. And you say, excuse me, I haven't, how would you find P star? And they'd say, run Newton's method. But if you run Newton's method to find P star, now you know exactly how many steps and you don't need an upper bound on it. Is everyone following this? Like how ridiculous this is, right? Okay, so all I'm doing is I'm just making fun of the way this is normally discussed and taught and all that kind of stuff, because we're going to fix it next time. In fact, we're going to get a little bit, these are just the hints of what's going to happen. Here's our little example like this, and you can see exactly what's happening. What's being plotted, at least for the first two, is the actual, it's the ellipsoid determined by the Hessian, right? And you can see, by the way, in this first one, maybe it's not quite right, right? Because it's, you know, maybe the correct Hessian change of coordinates would be this, but it's a little bit like that, right? So, and you can see by the time you get down here, by the time you get down to this point, you're actually applying the correct local change of coordinates. And the thing you want to focus on here is the axis. This is 10 to the minus 15, right? So what happens here, now unfortunately this thing goes into quadratic convergence almost immediately, but we'll see a bigger example, maybe on the next slide. Yeah, we'll go, yeah, here we go. Here's an example in R100. This is very typical, okay? So here's exact line search, backtracking, and what you can see, the scale here is covers 10 to the 20, right? So you have to understand how to read the scale. So what happens is, you know, this is sort of the region of linear, that's the damped convergence, and when you get the undamped phase, here's what happens. You can see that this thing is going down quadratically, right? And I mean, it's all over at 10 to the minus 12, right? That's at that point, you're double precision stationary, and there's nothing more to do, right? Actually, if you run it some more, you would get things that look like this, right? I mention this because you will be doing it, and you might get that. What would that be when you see that? What's happening is, what you're looking at, these numbers would be so small, you're looking at just the round-off error from floating point numbers. That's what you're looking at, okay? So if you see that, then back off and don't plot and clip your graph higher. Okay, because it's unattractive. Okay, and I mean, you study this in another class. I mean, look, it's all over. There's no optimization problem where you actually have to worry. If you're solving an optimization problem and you actually have to worry about the 8th digit, that's impossible. Let's just leave it that way. Okay, it's not good, right? If whatever your real application depends on the 8th digit, just go home because it's all over. Okay, so here's a big one, just for fun. Just to show you that this persists in higher dimensions. So here we're minimizing, I don't know, some big old log barrier type thing. This is in R10,000, okay? Here, and this is a good point because I'm going to get to quiz you on some things momentarily, but let's see. So here you're minimizing this thing. That's the log barrier, by the way, for the unit cube, right? And this is the log barrier for some polyhedron. It's a polyhedron in R10,000 with 100,000 faces. Okay. How many vertices does that polyhedron have, by the way? Basically, probably more than the number of subatomic particles in the known universe. Okay. Maybe with or without the dark matter. I don't know. It's big. Okay, is the point. So, all right. So, and here it is. This is on a huge scale, right? So for all practical purposes, I mean, you're probably done like right there, but. And here it is, and you see exactly, it persists. You see this is sort of that sort of linear convergence. When that thing rolls over like that's when you declare success, and you've achieved quadratic convergence, okay? And what you'll see at the same time, if you plot the damping factor, the TK, the step size, it should be 1 from then on, right? If you see anything else, it means you messed up or something like that. Right? So that's it. So this works. By the way, this requires solving a system of the form this. Right? We had to calculate the Newton step each time. We had to calculate that. That matrix is 10,000 by 10,000. Maybe this is jumping a little bit ahead, but why this runs really fast? Guess why? You can kind of guess. I don't know if you can do this. In your head, you can say what the Hessian of this first term is. It's diagonal, right? Because it's a sum of functions of xi alone, so it's diagonal. This one, these are sparse, right? So we indeed computed this thing, but we're relying on this thing being sparse, right? Without sparse, oh, we could do it. It'd be way, way slower. I pointed out something very awkward, and that was this, that we were in a weird situation where the code was more sophisticated than the mathematical analysis, right? Because the code was actually affine invariant for Newton's method. In other words, if you scaled things, except for second order effects, which would be just like numerical errors, you would generate the same sequence. But the mathematical analysis was not affine invariant. If you changed the coordinates in the mathematical analysis, everything changed. There were numbers like little m, big M. The Lipschitz constant changed. That was the critical thing that told you how big the third derivative was, right? So this is awkward, right? Because it should be the other way around. It should be that the math is clean and beautiful, has beautiful aesthetics, and then the code has got all sorts of hacks in it, and you shouldn't look inside it because you didn't want to see it. Okay, that's the way it should be. So this was fixed. This was fixed about, I don't know, 15, 20 years ago, something like that, by Nesterov and Nemirovsky. So, and once, with all the background, you could almost guess what the solution is. So here's the background. This is before we get into anything, just what it is. So what we're going to do an analysis. What we want is an analysis of Newton's method that, like Newton's method, is affinely invariant. That's what we need. Because, I mean, aesthetics demands it, right? So now let's think about what that means. Newton's method works well when the third derivative is small. That's the point. If the third derivative is 0, your problem is quadratic, and Newton's method works in one step. If it's small, then it means that the quadratic approximation is a good approximation, and Newton's method will work well. Okay, everybody remembers this. And in fact, you should remember that Newton's method, in the classical analysis of Newton's method, by Kantorovich, then the third derivative being small was expressed through the Lipschitz constant L on the Hessian, right? That's essentially a bound on third derivative. Okay. So the question comes down to this abstractly, and the answer will almost like pop out by itself. If you just saw the answer's on the next slide. If you just saw the answer by yourself, you'd say, oh my God, like who would ever think of such a thing? I mean, the answer being Nesterov and Nemirovsky, but so the question is this. How can you express the third derivative being small in a way that is affinely invariant? So that's what it comes down to. Because if you can do that, you can analyze Newton's method now in a way that is affine invariant. Everybody got this? So here are things you cannot do. You cannot say something like this. You cannot say, f prime prime prime. I'll just take the scalar because it doesn't matter. You cannot say the following, right? That this, is less than some number. I mean, like 1 or 2 or anything. You can't say that. Why? Because if I change coordinates here, for example, if instead of f, I look at f of ax, right? The third derivative will change by a cubed or something like that, right? The third derivative, this would be a cubed. And that says that by doing a change of coordinates here, I can make the third derivative any number I want. And I can make it as small as I like or as big as I want. Everybody got this? So this kind of ruins everything, right? Because it says that the third derivative is not affine invariant, the magnitude of it. Well, okay, duh, right? So this would be something like L. Okay. So then the question is, how can you say the third derivative is small in a way where whatever that definition of small is, it will hold not just for f of x, but f of ax. Yeah, this is the, a is, well, okay, that's the change of coordinates. Change of coordinates in R is very simple. It just says scaling, right? So you have to have a scale invariant way to say the third derivative is small. And if you think about it for a long time, only one thing could possibly come up. We'll get to that on the next page, but we can almost sort of invent it right now. This thing will scale like a cubed. This one, that's the second derivative. Here, this thing is going to scale like a squared. That is always non-negative. And so one completely reasonable thing, in fact, there really is no other choice, is to do something like take the third derivative or the second derivative and take it to the like 3/2 power. I mean, that's how you convert an a squared to an a cubed. Right? And you could do it another way. You could take the 2/3 power of the third derivative. Everybody following this? I mean, so All right, so all of that just came from aesthetics. It said, let's figure out a way to say the third derivative is small, which, however, is invariant under scaling of the argument. Okay, so that's, everybody got that? So that's it. Okay, so that's the background. So the next slide is not going to be a shock, but let me say a little bit about it. So self-concordance is the name given for a condition. You're going to see it on the next page, but it's basically this. And what's going to happen is it's going to remove all the shortcomings of the classical analysis, right? So something is self-concordant. It's not going to depend on any constants that are unknown. It's not going to depend on any constants which change when you change coordinates. It's going to be completely independent of it. So in other words, we're going to make our mathematical analysis affine invariant the way the actual algorithm is. Okay. Now, what's going to happen is we're going to get a special class of convex functions. These are going to be called self-concordant functions. They're going to satisfy this property. So it's not going to be all convex functions. And for these special functions, self-concordant, what's going to happen is we're going to have a very streamlined analysis of Newton's method. And it's not going to be like one of these classical Western convergence theorems that says if, and then a long string of things, not one of which you could ever check, holds. Then a long string of things, not one of which you could actually care about if you were actually solving problems. Here it is. A function on R is self-concordant if the absolute value of the third derivative is less than 2 times the 3/2 power of the second derivative. Okay? So that's it. Now, without the discussion we had earlier, you would have looked at that and said, I mean, I remember I did. And it wasn't written that way, by the way. It was written in much more complicated notation. And you would look at that and go, what? Where did that come from? But it's kind of clear. This is the idea. And if you like, this could be a Lipschitz constant. By the way, why is the 2 there? You could replace 2 with any other number. All the analysis would work fine. 2 happens to be a number that works for a lot of common functions, right? So we're going to see that. Okay. So the 2 is there, again, for aesthetic reasons. It's more or less the same reason why in front of a quadratic, you often put a 1/2, right? Just aesthetics, because you take gradients and it goes away, and I don't know. Okay. Now we say a function on Rn to R is self-concordant if the following is true. You restrict the function to an arbitrary line, right? So f is a function on Rn, g is a function on R. If that function is self-concordant, right? So if it satisfies this, if g satisfies that, then you define the function to be self-concordant. Okay, so that's the idea. And it's a way to say, I mean, the correct way to think of this is a method to say that the third derivative is small, but it's a method that is invariant under scaling. Very important. Okay, so let's look at some example. Well, look, linear and quadratic functions, f prime prime is 0. So, I mean, of course, right? Of course, the theory of Newton's method applied to linear and quadratic functions is a pretty short theory. So, and we don't need a theory of it, right? So, anyway. But the following is true. If a function is well, we'll get to that in a minute. Okay. So, negative logarithm. There's a function that comes up all the time. And, how do you verify these things? You just check. You take the derivative is -1/x, the second derivative is something, and then you get a q. In fact, you get something like x to the -3 with some number in front. You take the 3/2 power of whatever the second derivative is, and you just verify, okay, that it holds. Okay, so that's the negative logarithm is. Here's one. It turns out negative entropy, that's x log x, that's not self-concordant. But x log x minus log x is. Okay, so that's self-concordant. And there's a reason for that, because self-concordant functions will actually automatically be barriers, right? So if they're not 0, they'll be barriers. Okay, so and that adds the barrier. You'll remember that x log x is not a barrier because it goes to 0 at x equals 0, which is the boundary of the domain. It's not a barrier because although the slope gets infinite, goes up like this, it stops at 0, and it's not a barrier. And that means, by the way, it violates one of these rules we have for whether one of these unconstrained methods works, right? Which is that the sublevel sets are closed. Okay, here's the most important part is this, and this is kind of obvious. It says, let's scale the argument. The translation, of course, totally irrelevant, but let's scale it by a. Then it says that we'll call that f tilde, and we'll calculate f tilde prime prime. You get this, of course, and this is that. And of course, if I take the absolute value of this and compare it to the 3/2 power of this thing, then the a's just go away. And so the point is that self-concordance is just what we want. It's a way to say that a function has a small third derivative, which is invariant under scaling. Okay? So, by the way, it is not at all invariant under scaling the function on the outside. So 2f, if f is self-concordant, 2f need not be. Okay? But actually that's not the real issue, is whether you can scale a function like that. In fact, you wouldn't want to, because a complexity analysis based on scaling a function outside would be nonsense, right? Because one of the things you're interested in is when are you within epsilon of the solution? But if I'm allowed to scale the function itself, I can make anything have any error, right? So, okay. So there's a whole calculus of self-concordant functions. And here's one. You can scale a function, but only by something more than one. Okay? The sum of self-concordant functions is self-concordant. By the way, that's not obvious. I mean, you actually have to kind of show those things. It's not, you know, it's kind of classical analysis, right? You sit down and you work out some stuff, and there's some, you know, polynomials and some various inequalities, a couple of Cauchy-Schwarzes later, or however you do these things, and the next thing you know, you have it, right? So, but it's, you know, it's kind of like pencil and paper kind of stuff, right? Okay. It's preserved under composition with an affine function. That's clear. In fact, that's completely clear. So if f is self-concordant, so is f of ax plus b. That's pre-composition. One way to generate a lot of them is, it turns out that a lot of functions end up looking something like this. It's the log of something is self-concordant, right? And so a general theorem for that says that if the third derivative of a function is less than, you know, 3 times the second derivative divided by x, I mean, these are just obscure, weird conditions, right? Then this function is self-concordant. That allows you to show a lot of things are self-concordant, right? So, so let's look at a couple of examples. Here's one, the log barrier. That's self-concordant. Why? Well, because, you know, the minus log is, right? And then minus log of affine is, sum is done. Here's one. This is not obvious at all, but it's true. Negative log det x. That's that's actually the barrier for the positive definite cone, right? It's also related to all sorts of things. It's like entropy of a Gaussian distribution. It, as a function of the covariance, it has to do with volume of ellipsoids if we're doing a geometrical problem. So this comes up in tons of things, right? And not only is minus log det x convex, it is, in fact, self-concordant, right? By the way, this would not have been so much fun, right? So, for example, the third derivative of minus log det x is it's something that could easily give you a little bit of a headache, right? Because it's a trilinear form on symmetric matrices. So it's a trilinear symmetric form that takes 3 arguments, right? You know, A, B, and C. And it's so anyway, I just put it this way. That's 6 indices, okay? So if you're good at that or whatever, great. But 6 indices is like several past my own limit, I can tell you that. Here's one. That's a convex function of both x and y. That is actually the log barrier for the second order cone, this thing. By the way, bits and pieces of it do not look convex, right? Here, right? So for example, the y squared looks deeply suspicious, right? Because how could this be convex in both x and y? Because this is kind of weird, right? Look at that. That's quadratic in x, but there's a minus sign. That's quadratic in y, but there's a plus sign. So, but it is. This is convex, and actually you've seen it before. But it's not just convex, it's actually self-concordant. So, okay. Now let's look at Newton's method. All the details are in the book, so but we'll just see how this works. Remember how Newton's method worked in the classical analysis, which, by the way, also came from Moscow. So here's the difference is this. This says you look at the Newton decrement, that's lambda of x, right? And it says the following: if it's bigger than some number, and you know, you can get super duper explicit about the number. It depends only on the backtracking parameters, right? So you get things like, if you tell me whatever alpha and beta in your backtracking thing, I can tell you what eta is, and it'd be like 0.16, right? And so you even see cool papers like that, where there'd be things where if this is less than 0.16, and you're like, where did that come from? Anyway, so the point is, if this Newton decrement is bigger than some number, then the following holds. The function value goes down by at least gamma, right? And gamma is an absolute constant. I mean, they only depend on, you can work it out and you can evaluate it, and it's just a number. It depends on absolutely nothing you don't know. Well, I guess the prior knowledge here is that the function is self-concordant. So I guess that's something you know. But you already know a whole bunch that are. Okay. The second is this. If on the other hand, once this Newton decrement gets less than this critical value eta, then the following is true. 2 times it is less than 2 times it squared, right? By the way, this kind of hints, this one maybe, that we would have improved aesthetics if instead of we define the Newton decrement as lambda, maybe lambda over 2, right? Because then this would have been really super duper pretty. It would have been something is less than something squared. But remember in the other one, in the classical analysis, you had things that looked like this. I mean, this thing basically says that the error at the next step is less than the square of the current error. But in the classical analysis, there's all sorts of other crap in here involving like little m, big L, all sorts of stuff you don't know. Now, that doesn't matter if your idea of a convergence proof is that it's a feel-good thing, right? That kind of, vaguely justifies, your method or something, right? Then that's fine, because you don't know those constants. And anyway, so here, though, it's not. It's just, there it is. It's just, there's nothing there. And so the complexity bound you get is shocking. It's just this. It says it's f of x0 minus p star. That's how suboptimal you start, divided by gamma, plus log 1 over epsilon. That's it. There's absolutely no constant in there you do not know. It's just, that's just a number of bounds. Okay. Now, if you take the simple analysis, the one we have in the book or whatever, and plug in various things, this bound will come out to be 375 times f minus p, suboptimality, plus 6. Okay? Oh, by the way, I would usually write that as 5 or 6, just for fun. Mostly to irritate people who do complexity analysis. But and it works, by the way. I can recommend that. Well, wait a minute. You look at this thing and you go, that is so cool. There's nothing there you don't know. Oh, wait, there is something you don't know. Wait a minute. You don't know that. And you'd say, oh, well, okay, that puts a little bit of a hole in it there, right? It's 375 times how suboptimal you are. And then you say, well, how would you get p star? Well, you might run Newton's method. Okay, but once you run Newton's method, you do not need an upper bound on the number of steps Newton method because you just figure out, you just record how many steps it took. Am I capturing the, okay, good. So, all right, so what I'm going to say, this is going to be super vague now, and it will not be vague on Thursday. So here it is. Have you ever heard of any method by which a person can get a lower bound on p star? Let's just admit freely that, yes, there's a number in here we don't know. It's p star. And then we're going to say somehow when we actually use this for something, the way it's going to go down is duality is going to come on. And we'll have somehow we're going to get a lower bound on p star. By the way, this is a kind of a sloppy bound. If you do a very careful kind of Russian style bound, right, this number comes down to something like 10.5 or 11 times f minus this plus the log thing, right? So instead of like half a page, that's like 6-8 pages of some pretty crazy stuff, right? But that's not bad. Okay. So something very interesting happens, and this is worth looking at. Here it is. Here's a log barrier. That's a self-concordant function. Oh, of course, 2 or 3 times this is also self-concordant. So I think probably the right thing we should say about this problem is this function is that is minimally self-concordant, meaning if you divide it by any number, if you scale it down, it won't be self-concordant, right? So that's kind of the idea. Because I could multiply this by 100 and everything would be off, right? So, all right. Because actually what happens is what scales is f minus p star. F of x0 minus p star would scale by 100 and we get a totally, well, it would scale the wrong way. Okay, so that's a minimally self-concordant function. Now, what's here is this. We generated kind of random instances of this. And then with random numbers for n, m, and then we used Newton's method to solve it, whereupon we recorded the number of steps it took. Okay? And what this shows, whereupon we recorded 2 things, of course. The actual suboptimality, because once you run Newton's method, you know what f of x minus p star is. And you also know the number of steps, and you just make a scatter plot. And you get something like this. Okay? So now, what the self-concordance analysis tells you is this. It says that's an upper bound. And the good news, now that would be a function that looks like this. It starts here and then basically goes up with infinite, it looks like that. Oh, that didn't come out right, but you know what I mean. It starts at 6 and goes up with a slope of 375, okay? So, and good news is all of these are below that, okay? The better Russian bound, the Nesterov-Nemirovsky bound, you put a 10 in there or an 11 or something like that. And now your slope is, it's not so bad. It looks more like, I don't know, something like this, right? I don't know, like that. Okay. But what you see hints at the following. It suggests that it kind of works with C1, right? That's an empirical estimate, right? Oh, and by the way, how do you explain that and that and that? What are these points? Dumb luck. Okay, so this was a case where you were quite far from optimality, and your Newton step, well, it only took 10 steps. So what happened was it kind of went there, it went there, and just accidentally found itself, after like 2 steps in the region of quadratic convergence, and it was all over 4 steps later. Okay, so these are dumb luck, and of course that's going to happen, right? By the way you know it's going to happen is you can do things like run Newton backward and stuff like that, and so you'll quickly get far away, and so that means that in all of space there will be points where dumb luck will prevail. Okay, so but what's kind of cool about this is what's wonderful about it is this. It says that we can actually have 2 discussions about the complexity of Newton's method, and both discussions work like this. It says I can have an actual mathematical discussion. I plug in c equals 11. And of course, I'd explain that 6 is a macro for log 1 over epsilon, right? So if I replace 6 with log 1 over epsilon, I put 11 for c, and then it's actually a true statement. That is an upper bound on the maximum number of Newton steps it can take. And that you can say that in the math department, no problem. Okay? So that's one thing. But the other cool thing is, you can also talk, you can divide the audience in 2. People who just care about, look, how many steps is it going to take? On average or typical, what can I expect, right? Then all I do is I change c. I change it to 1. And it's kind of an empirical upper bound. I mean, change it to a half, and it's probably a good estimate of what it is, or 3/4. Everybody see what I'm saying? Right? So it suggests that things based on this, you can have a dual discussion. You can be talking to the people who want to do math. There's nothing wrong with that, the people doing complexity analysis. And you can also, at this exact same time, be talking to people who just say, how should I choose alpha and beta in my thing, or something like that, right? In which case, you could minimize this with c equals 1, and this would kind of give you a reasonable way to do it. Okay, so let's talk about implementing Newton's method. Now, you're going to use linear algebra. Now, this is it. And this is where actually knowing linear algebra, numerical linear algebra, is actually very important, right? Because, yeah. In fact, I should give you some of the history. So, Newton's method, well, the name suggests that it was not invented 20 years ago. Okay, it goes, and Newton did the one with 1 variable, and then in the early 19th century, it was extended by Raphson. This is the British-centric view of how the world went. I'm sure there's other versions of the history, and so sometimes Newton with more variables than 1 vectors is called Newton-Raphson method. Okay, but now we're in the early 19th century or something like that. So this is not new. Oh, by the way, many variables in 1850 or whenever Raphson did this would be like 3 or 4, right? Because, by the way, if you are, that would be like a super big problem, because guess how you solve linear equations in 1840? You know how to do that. We fast forward to let's say to the early computers. So it's the 50s, it's the 60s, right? And there, it was a big deal to solve a system of linear equations with like 100 variables and 100 unknowns. That was a really big deal, right? That's right. So in fact, there were people who had, the same old story, like maybe the world market for computers will one day approach 6 or something. I don't know. It's the same sort of thing with linear equations, that people said things like, well, you can imagine possibly solving 100 variables with 100 unknowns, but it wouldn't seem to have much meaning, or you can't imagine that, right? So, okay. Of course, people say this all the time, right? Or they make that kind of statement. Okay, so in the 60s, and this was mostly in the West, what happened was Newton's method kind of went out of favor. And the reason was everybody focused on, oh my God, you have to solve this equation here, a set of linear equations. And you wouldn't want to do that for more than 100 variables, right? So that was the argument. And there are actually a whole bunch of methods, which are actually quite good methods. In fact, a lot of them are called quasi-Newton methods, and the whole idea is to get around this terrible task of solving a system of linear equations. Everybody got this? Now, of course, these days, that's all nonsense. You go up to a couple of thousand, and it's not a problem on a laptop, right? It's a non-issue. But what it misses is the following. If there's any structure in the Hessian, that's where smart linear algebra comes in, okay? And so we're going to look at that. And so there are lots of cases where people say, well, we would never use Newton's method. And you look at it, and the Hessian is like, banded plus rank 5. And you're like, I can actually do an iteration in about 80 microseconds. So again, if you know what you're doing. So, okay, let's move on. So how would you do this? A very good method would be this. You just do a Cholesky, you form the Hessian, do a Cholesky factorization. And it turns out, by the way, that the Newton decrement is one of the parts of this. I mean, not surprisingly, right? It's the norm of L inverse G. That costs, n cubed over 3 flops for an unstructured system. And if H is like sparse, right, a specific case of that would be banded, this is way less. For example, if it's banded, this is O of n, right? So that means, for example, on that laptop, this laptop here, I can easily knock off a Newton step on something where the bandwidth is 10 and it's a million variables. I can knock it off in, I don't know what, I have to do the arithmetic, but it's way it's measured in milliseconds, okay? Whereas if you don't know that, I mean, you're cubing a million and, incorrectly concluding Newton's method is useless. Everybody see what I'm saying here? So this is why you want to know about linear algebra. This is why you want to know about numerical linear algebra. Okay. All right, so here's an example. And in fact, this is the last thing you have to do. There's one more thing, but it's related to it. You should know some numerical linear algebra. And that means that there's a part of your brain that's all set up now, and like it should release endorphins when you see things like arrow matrix, right? You should look at that and go, oh, yeah, oh, God, that's great. Oh, you should, right? Everybody know what I'm talking about here, right? If you see things that are like, I don't know, diagonal plus low rank, you should say, oh, boy, I know, step back. I'm an expert. I know how to handle this, okay? Everybody? Okay, you know what I'm saying? So these are all the things. So you should understand, sparsity and things like that, and this should give you a good feeling and stuff like that about how to, that there's something you can do, right? Some problem is on a graph. If there's a sparse graph and you look at it, okay. But the next thing to do is to relate that back to the optimization problem, right? So, and specifically Hessians. So here's an example that shows you how to that tells you how the structure in an optimization problem translates into sparsity pattern in the Hessian, or structure, not just sparsity pattern. Here's an example. Let's take a function which is this. It is a sum, it's separable, that's a separable function, right? By the way, this could be regularization. That could be an L, well, it's not an L1 norm because we're doing Newton's method, but it could be some kind of regularization, right? Some function of the individual things plus a function of a linear, of an affine combination. Okay? Now, a function like that, if you work out what the Hessian is, it's this. The Hessian of a separable function is diagonal, right? Why? Because, I mean, partial xi, partial xj is 0, right? If you take partial xi, you get, phi prime of xi. It has nothing to do with xj. So basically, I mean, so these are the maps you want to make in your brain. That things like separable means diagonal Hessian. By the way, what does block separable imply? Block separable means I can chunk my vector up into chunks, maybe 5 long, or it doesn't matter. I chunk it up, and my function is a sum of functions of those chunks. What does the Hessian look like? It's block diagonal. And block diagonal would be one of the things that should be triggering endorphins, at least in the section of your brain that does numerical linear algebra, right? Because it's way easy. You should say, I can solve that fast, right? Because you can, right? By the way, why is it you can solve block diagonal things fast? You can do blockwise inverse, and so you could say I could do blockwise inverse. I could do it all in parallel, right? I could have different threads doing each one. Yeah, all these things are true. But maybe another way to say it is this: if the cost of solving a block, it's like n cubed. It's convex. it follows instantly that if you break it up, you're going to do better. So that's it. So it's actually convexity that tells you that. Right. So, okay. Now when you see this, something like that, the Hessian is this. There's just simply a formula for the Hessian. H0 is the Hessian of the psi here, psi 0, evaluated at ax plus b. By the way, this formula for the Hessian, these are things, they're sort of, we put them in kind of an appendix of the book because it's a pain to work them out. And I'm going to give you some very practical advice, so please listen now. When you see something like that, like a log barrier, you might want to do something like calculate the Hessian by hand. Why not? It's just a second derivative. How hard can it be to calculate partial xi, and then after that, partial xj? It's reasonable, right? And by the way, at the end of the day, I mean, this is probably not a bad thing to, I mean, you should check it, right? If you, or whatever. I mean, the ones in the book are correct, so you don't have to check those. But, anyway. Everybody see what I'm saying? Okay, so here's my advice, very practical. Yeah, don't do that, okay? You will be very sorry. Use the chain rule absolutely whenever you can, right? So usually, psi 0 is something real simple, right? Like psi 0 could be something like, the square root of 1 plus, y transpose y. There you go. That's a nice differentiable function. That's psi 0 of y. Okay? Now, that, go ahead and take partial yi, partial yj. Please do, right? That makes sense. But the minute you put these a's and b's in there, there's no way you're ever going to come out of this with anything correct. So, okay. So, and by the way, I sometimes have to remind myself this because I'll look at something, I'll start taking partial derivatives, and then I'll hear my own voice saying, don't do this. You're doing something, don't do this. So, okay. All right. You can, anyway, trust me, this will be relevant for you at some point in the near future. So, okay. So the point is, here, now you stare at that and you realize that if A is, if A here is wide, right, then that's low rank, right? So a function of a low-dimensional affine function, the Hessian of that is low rank. In fact, the rank is exactly equal to the size of the intermediate variable, okay? So I'm just, and there will be other things that you will connect and things like that, but you want to get a mapping from a problem to sparsity patterns. And then, of course, once you know about sparsity patterns, you want to understand how to exploit that sparsity pattern in solving linear equations, right? And so this will take you quite far. Okay. So here, I mean, of course, this is the message, right? Dumb linear algebra says H is dense here. Of course it's dense, right? If you add a low rank thing to anything, it's going to be dense. I mean, with high probability, right? So yeah, and then you do this and it's like n cubed or something like that. But if you do the right thing, which is just exploiting the diagonal plus low rank, you'll end up solving this in actually linear in n as opposed to n cubed, okay? And this is a big difference, right? Because n and, problems are not interesting until they have about 1,000 variables or more, and they can have a whole lot more. And so if you take here n equals 100k, this gets super interesting, right? So it says that problem, I mean, if the height of A is 10 and n is 10,000, that's easily within striking distance of a laptop, maybe even a phone. Okay, so but for that you have to know linear algebra. You actually have to know linear algebra. Okay.